We come to our final talk in this morning's session. Our next speaker is Professor John Bridges from the University of Leicester. He has kindly brought some sample meteorites, I believe, which I think are sort of making their way round. So if the person next to you that you've never met before starts to get a bit friendly, that's probably what it is. John, the formation of the planets. What have we learned from such samples and meteorites? Thank you very much indeed.
So we're going to continue zooming in into our own solar system, and my brief is to talk about what we have learned from sample return missions and meteorites about the origins of our own solar system. So I'm going to talk a bit about meteorite types and their parent bodies, and hopefully there'll be something for everyone here, some cool images and some results, so hopefully you can sort of pick and mix. And I'll talk a bit about some aspects of how this has informed our current models of planetary formation, the early solar system, water on Mars. So it's a vast range of topics, really, about the evolution of our solar system that are tied in with this topic today. I'll focus on the runaway growth rapid accretion model for the formation of planetesimals and into our planets, and some of the evidence and some of the implications for that, and a little bit about the heat sources and the implications of that for the early solar system. And then I'll finish up talking about some past and planned sample return missions and how that ties in with this work. Okay, so most meteorites, the vast majority are fragments of near-Earth asteroids, and those are two classic ones because they go back, or they fell over 200 years ago, just when it was recognized that this wasn't just folklore, these really were extraterrestrial objects. A very important one, okay, carbonaceous chondrite, a bit more about that later. Here's Siena, 1794 in Italy. Again, one of the first ones to be seen to fall and recognized as an extraterrestrial object. So a few key points. Fusion crust, that's important. So when meteoroids and then meteorites come through the Earth's atmosphere, it's really only the outermost fraction of a millimeter, the fusion crust, which melts and fuses very rapidly. The inside, happily for us, stays cold and unaltered, and by the time the meteorite hits the ground, it's cold as well. So the great thing is, although they've had this traumatic journey from the planets and the asteroid belt, the inside has stayed pristine and gives us this remarkable record. So I'm going to talk about some of the mineralogical record in particular within it. Okay, so the vast majority are from asteroids, but we're recognizing hundreds more from Mars, Moon, and Vesta. Okay, now, perhaps if you just want to take one thing from this talk and then enjoy some of the pictures I'm going to show, is probably this one. This is why we study meteorites, okay? This is why they're important. So if we compare the composition in Auger and some of the most primitive carbonaceous chondrites, compare that to observations of the solar photosphere, putting aside hydrogen and helium, so we're interested in metals as such, there's this nice one-to-one correspondence. So when we study these, we're looking at the building blocks of the solar system, what we're made of, and then how everything has differentiated from that, okay? Okay, and this has some direct implications for some of the source materials, the planetary embryos for our planets. I'll give an example of Mercury and how we can relate that directly to some of our meteorite types. And the age of this, well, we don't have time to talk about many topics, and we don't have time to talk about radiometric dating, but all this was basically kicking off 4.57 billion years ago as previous star generations started to collapse into our solar nebula. How do we get the meteorites here? They start off largely in the inner and outer belts of the solar system. Then, because of the Kirkwood gaps, There's resonances between the period of the asteroid and Jupiter. Those are unstable, so there's a short lifetime, and ultimately a fraction end up in near-Earth crossing orbits. I won't dwell on this, but there are well-known physical processes, the Okosky drift, for moving asteroidal material around the solar system. Okay, so here's our classification tree, okay? And this has really been built up, and the UK has played a large part in this, through the 20th century. It goes back to someone called Pryor in 1911. He recognized the importance of whether the iron was metallic, and if you can see that sample, if you hold it up, you'll see the shiny metallic material, okay, and the iron which is oxidized in silicates. And that's largely the basis for classification of the chondrites here, the most abundant kind. And there's a lot of detail here, but basically we look at things like the mineral compositions, the proportion of metallic iron, and things like chondral size, more of that in a minute. And so we can work out that we think there's well over 100 sort of distinct parent bodies in the solar system. There's okay again, just showing there's the fusion crust and that dark, largely dark interior because of all the carbonaceous material. Sometimes with carbonaceous chondrites, you can actually smell them. But here, when we start doing a sort of deep dive into them, we can see a more complicated story quickly starts to emerge. So we've got that one-to-one relationship with the bulk composition of the solar system. So is that it? Well, no. So one of the mysteries about chondrites is that when we look down at the millimeter, micron, down to atomic lattice scale, then we start seeing these melt droplets, which will form at maybe 1400 degrees Kelvin. So iron, magnesium, silicates in these, which must have crystallized relatively rapidly. There are also, here we see some in an electron microscope image, we see clays, carbonates, iron oxides, which need water, liquid water. So what on earth is liquid water doing on a small planetesimal? What are the heat sources? So a lot of mysteries here. And I do recommend, do have a look at the virtual microscope. There's really fantastic resource, lots of images, all sorts of different meteorite kinds. Okay, so here's a section a bit similar to some of the ones which are coming around. This is a carbonaceous chondrite. So I put this in here because it shows about 70% of this chondrite maybe, or even a bit more here, are these melt droplets and what we call calcium aluminium rich inclusions. That's getting a bit sort of meteorite nerdy, dare I say it, but bear with me because that does show all the processing that's been going on. So there's a lot to be learned about what was happening 4.6 billion years ago from these. Okay, there's one closer to home, Northern Ireland. That's type 3, and those are some of the least altered. So we just see these beautiful textures, these large clasts, which we don't fully understand how they formed. Perhaps on some of these planetesimals there were what we might call igneous processes, and those millimeter melt droplets, which have all aggregated to give this, this bulk solar system primitive composition. Okay, so we start delving in. So in our sort of analytical chain, we take electron images, a backscattered electron image here. We see that the bright metals and those silicates. There's a very famous one, an Indian one from the 19th century called Semacona. So we tend to focus on the most pristine, the least thermally altered ones to tell us about what was happening on those planetesimals. There's just one of Allende, which is carbonaceous chondrite, and there's all sorts of other processes going on. We'll show some images of asteroids later, and so sometimes we get preserved what are called rubble pile textures, and these also have this bright blue, because of cosmic ray radiation, halite rock salt crystals, again showing that Curiously, there was liquid water on these planetesimals. So all sorts of different processes, textures, quite a dynamic sort of environment 4.6 billion years ago. I can't give a talk with this brief without mentioning Winchcombe. 2021 in Gloucestershire, tying in with sort of modern way of identifying meteorite falls. The traditional way, most meteorites have been found in Antarctica or more recently Northwest Africa, but increasingly, because everyone's got a camera on their front doorbell and in their car, etc. We've got now these fireball networks, and for instance, we've got one on the roof of University of Leicester, and that helped a lot with locating the Winchcombe Fall, which is a carbonaceous chondrite and famously fell on someone's front drive. I think you can see that at the Natural History Museum now. So we start analyzing it, going into progressively greater detail, and so we pick out all the different mineral assemblages, which will tell us the temperature, brine compositions, all sorts of things we need to start unpicking to find out what was happening on those planetesimals. Okay, I put this slide in not because I want to suddenly make you all into electron microscopists, etc., but just to show when we start digging into the detail, then we'll take our sample returns and our meteorites to the big national facilities like the Diamond Synchrotron and transmission electron microscopy. So we get down to the atomic lattice scale. And the reason we do that, because we need to identify in detail the mineral assemblages to get all the information that we require. Okay, so I've got a sort of mineralogical bias today, but no talk like this would be complete without some mention of stable isotopes. So here's another sort of alternative map of the solar system for you. It's based on the 3 stable isotopes of oxygen, the most abundant one, oxygen-16, and then the less abundant O18 and O7. And the Earth lies here, and there's Mars a bit displaced from it. You can think of this as sort of the end product of mixing. So all those interstellar grains, the original molecular crowd, sampling different stellar generations, they've sort of, to some extent, not entirely, homogenized within this central part. If we were to include interstellar grains, which we sometimes find in chondrites, that's a whole different talk, then we would see values, right up here, right down there, etc. But all these have mixed. But some of the parent bodies, like the carbonaceous chondrites, haven't entirely homogenized with the rest of the solar system, so we can identify different parent bodies and make links with our planets. Okay, so a lot of the work on meteorites and related analyses is fed into what certainly in sort of planetary materials world we use as our sort of, if you like, general model for runaway growth of the planets, planetary differentiation as you go from a primitive, undifferentiated body into a body with core, mantle, crust, etc. So I'll talk a little bit about that and how we relate that to the heat sources that we need to drive all this. Okay, so we start with our giant molecular cloud to sample different stellar generations. It starts at slightly higher density, so it starts collapsing, rotating, and we get this sort of, I guess, fairly familiar picture that the nebula, pre-solar nebula, starts spinning, becoming more opaque, and then once you've reached 2,000, 4,000 degrees Kelvin, we start having the proto-sun, and nuclear reactions begin, and the solar system is well and truly on its way. Okay, so I'll give an example of the evolution of planetesimals, the building blocks at about 5 AU, Jupiter line. So we think really all the modeling points towards very rapid accretion, just of the order of hundreds of thousands of years. We start getting planetary embryos, including one that's 10 Earth masses as, if you like, a kernel for proto-Jupiter. And that was able to focus the hydrogen and helium in that part of the solar system, and hence we get the giant planets. Okay, so what did those rapidly accreting planetesimals look like? Well, this is when sample return starts coming in. So there's the Itokawa S-class asteroid, which was visited and sampled by the Japanese Hayabusa mission. And that's one of the things that we've been sampling in the UK and at Leicester. I'll give some examples. Okay, so there's our frost line, so at about that 5 AU point, and so beyond that, you start condensing the more volatile materials, ammonia, more of the water, noble gases, etc. Whereas in the interior, in the part of the solar system, it's a more rocky, more volatile part. Okay, this sort of was switched off by T-Tauri winds, within 10 million years as all that accreting hydrogen and helium was blown out. We're getting a little bit beyond my brief here, but just to point out, and I think perhaps we'll hear later this afternoon from Sarah Russell, that this feeds into models like the NEAS model for the change in planetary orbits and the dispersal of the original thick sort of proto-planetesimal belt to today's situation. Okay, so when you look at up at the moon and when you see Mars, Mercury, you're looking at late heavy bombardment as the movement of those planets deflected a fraction of those early planetesimals onto the surfaces of the rigid lithospheres that had emerged by then. Okay, but let's step back a little bit to a nice link between those meteorite types and planetary formation. So Mercury has about 70–80% volume of its dense iron nickel core. So this is very high density. So this is sort of one of the puzzles in planetary science, and there are sort of, if you like, two divergent theories. One, and you'll note perhaps a note of skepticism in my voice, because whenever there's anything in planetary science we don't understand, we tend to ascribe it to impact. But maybe you had a larger planet and impact knocked away more of the silicate mantle. But the alternative is that the starting blocks, the planetesimals, were much more iron nickel rich. And so one of the theories, quick heads up for the Mercury imaging X-ray spectrometer, which is on its way via Bepi-Colombo. We'll start mapping orbit 2026. Coming from Leicester, I have to mention that, okay? And so we'll be able to test these models. Is Mercury a planetary embryo dominated by this sort of very metal-rich chondrite? So that sort of model is largely driven by our work on meteorites. Okay, but hold on a minute. What's driving all this? So we've sort of asserted that there has been brines, hydrothermal action, melt droplets comprising 70–80% of some of these primitive chondrites. So, what's going on? We've got this strange dichotomy almost between the primitiveness and all that energy. Well, the main sources of the heat energy have really got to be dissipation of gravitational potential energy. Think of an accreting planet as material is accreting from distance, and dissipation of nuclear binding energy. And in particular, for today, the decay of the short-lived isotopes like aluminium-26. And that gives out so much heat, about 4 million electron volts for every decay of a aluminium-26 atom to the stable aluminium-26. And because it's relatively abundant, this is definitely a potent heat source, very short half-life, about 700,000 years. And so, assuming these early planetesimals, tens, hundreds of kilometers, were at least partially insulated, then there's really there's plenty of energy to explain some of those effects that I was talking about, those high high temperature effects I was explaining earlier, and the mobilization of liquid water. In terms of the gravitational potential energy, once you're into the planetary formation phase, just the formation of the core itself, the sinking of all that dense material. And so we've got these abundant heat sources, really. So we're accreting material from an infinite distance, and then gradually it's dissipated over time. You add in nuclear binding energy, you've got loads of heat within the first tens of thousands, hundreds of thousands of years to explain the sort of features that we see. So, in other words, really, once you've started the process with your solar nebula, you can't stop it almost. You've got this runaway growth, you've got abundant heat sources to drive the initial parts of the differentiation. Okay, so I think we can understand things like here's the Vesta meteorite visited by the Dawn mission, about 500 kilometers across. That's a type of stony achondrite. I know it's an igneous type of meteorite. So by the time you're up to this sort of size, certainly a differentiation you couldn't stop it. And then even on the smaller 100-odd kilometer sized planetesimals, the Semicona, again, there's abundant heat sources which will lead to the sort of textures that we're seeing. Okay, moving on rapidly to another parent body, Mars. So I'm going to cut to the bottom line and say, why did they come from Mars? Because I know that's what you all want to ask, so I'm going to get my answer in quick. And the reason for that is a sort of buy one, get one free offer from the landing missions. So with the Viking landers and more recent landers, including ones I work on, we've got the composition of the gases of the Mars atmosphere, and then when we analyze the gases in these meteorites, we see a one-to-one correspondence. So we see all sorts of types here, some classics of Nakhla, which fell in 1911, Chassagny, 1815, different kinds. So we study these, microscopy, we find clay, carbonate, everything we can do to piece together what we now regard as the ancient warm and wet environment on Mars, sort of over 3.8 billion years ago and older. And these meteorites and our landing missions are telling us about this. So we do a sort of forensic examination to look at the mineral assemblages and to determine the structure. Again, so planetary materials is a mixture of big, bold initiatives like sample return and then sort of careful, meticulous microscopy, isotope analyses, etc., to work out what's really happening. Now, you may have heard about Allen Hills 84001. So it was found in 1984 in Allen Hills meteorite field in Antarctica. And this was a source of great controversy. And this was about when I was starting off in mid-90s. And there were two brothers at the NASA Johnson Space Center, the Mackay brothers, Chris and David. Chris reckoned that those carbonate globules formed from microbial life, and he interpreted everything in that way. His brother, David, was vehemently adamant that they formed inorganically. So there's this fascinating duel which played out in the community. Ultimately, I think we all accept that it can be done here inorganically, but nonetheless, it was a great stimulus to Mars research. I think it probably helped with things like sample return missions that I'll talk about in a minute. So there's a bit of sort of serendipity or unintended consequences, but ultimately quite fruitful sort of science. Quite a wide range for Martian meteorites, but mostly relatively young in planetary terms, okay? And that's one of the reasons that we need sample return, because the Martian meteorite source regions likely fall in the younger regions, like Tharsis here in the northern plains, rather than the ancient highlands. So we've got this age and lithology bias. So that's why we're up here now, sampling for Mars sample return. Quick heads up, I think for this afternoon, Sarah Russell's talk, she's going to talk about lunar meteorites. But to get back to Mars, here's Mars Science Laboratory, and one of the things we do is look for meteorites. Or when we find a meteorite, we zoom along to it. It's a great environment, it's cold, dry, meteorites are well preserved there. So sometimes we see these, and we drive up and we see here a beautiful iron meteorite. So there's another part of our meteorite classification. So of course it's not just Earth that's experienced the flux of meteorites. I should note, really, that in terms of mass, most of the meteoritic material that reaches Earth and the other planets is in dust-sized particles. So there have been collections, for instance, on sticky plates on the wings of planes or from Antarctic ice holes. So this is another great way of finding out about the most primitive material. Couldn't resist putting this in, even though I know we're pushed for time, and that's because meteorite flux has been going on throughout the solar system. So just occasionally on Earth, in ancient sediments here, for instance, in Silurian, if you have the right preservation conditions, chondrite meteorites like the ones in the room now can be preserved. We get these beautiful ancient textures. So we tend to think of meteorites as sort of perhaps modern, recent things, but actually it's been occurring throughout our evolution of our planet. Okay, moving on to our sample return missions. So there's a lot to see here. Apollo itself, the big one, 400 kilograms. And again, that's a whole talk in itself. But we've got 3 from asteroids now. And we've got lunar sample return coming out. We've got Mars sample return. So there's an awful lot more that's going to be happening over the next few years. For instance, Artemis 3 and Mars sample return. Mars sample return, top of the NASA decadal priorities. It has had technical challenges, but, well, that's reasonable, really, I suppose. So now sampled 26 drill cores in Jezero crater from the ancient warm and wet Mars. And again, a lot of this was driven by our understanding from Mars meteorites. So we've got this nice feedback between meteorite research and our actual in situ analyses and orbital analyses. Right. So we're planning for that in the UK. So here we're working with the European Space Agency and NASA to get ready with our instruments and how to analyze these. So with sample return missions, we have to put a lot of effort into how to preserve and analyze these precious materials. Key thing is also asteroid-meteorite links. So we know we've got meteorites from some unknown asteroid. But the great thing, for instance, here with Hayabusa 2, we know it's spectral type, an S-class asteroid, and we were able to analyze it after it fell in Woomera and recovered in 2010. We started analyzing it. A lot of infrastructure needed. You need to keep it clean, low humidity, ultra clean, and very low static temperatures. So here's just a bit of context. We take it to all these, our analytical facilities, and the only thing I want to point out here is we've got a direct link between when we analyzed a meteorite type called Tuxtla, it's a stony LL5, and Hayabusa 2. So finally, we've got a one-to-one link here for our chondrites between a known asteroid type, an S-class, S for space-weathered asteroid, and our meteorite type. So we're getting this powerful link now between our 50,000 plus meteorites and known asteroid types. So that's a major part of the significance of this. Okay. So there, some of the techniques we do. Again, so we get down, so we're interested in looking at the micron scale, the atomic lattice scales, and sample return missions and fresh falls really drive that sort of work. It drives new instrumentation, new ways of looking at samples, new investment, dare I say it, from our funding bodies, we hope, from time to time. OSIRIS-REx, one of the more recent ones. First set of publications are coming out, and we're now moving into a sort of detailed phase of analytical studies. So that's going to be really exciting when we really start unpicking what this asteroid is made of, this B-class asteroid, and start relating it to our meteorites as well. Okay, I think that's up to my 30 minutes. So So a few things to pick out here, that meteorite analysis is central to our understanding of the formation and evolution of our solar system, feeding a lot of ideas, sort of guiding the nebula models, runaway growth models, etc. They've also spurred on sample return missions. Now, they're big, they're costly, but really, again, they give us unrivaled sort of access. So we do a lot on Mars with rovers, but it's really only when we are going to bring back the samples, similar to Apollo, that we can really get into the greatest amount of detail and reach the deepest understanding of the formation of our planets. Okay, so, and I hope I've shown that sample return missions are a great driver for scientific advances and changing our views of the solar system. So I think at that point, I hope you all have a chance, if you're interested, to have a look at some of those meteorites. I am monitoring eBay, so please don't put it on eBay. Back to you.
John, thanks ever so much. We have time for some questions, please. Are there any out there? One straight at the back there, please.
Hiya. I was wondering if there are any stories attached to the meteors you've handed around, or a particular reason as why you chose those two that have made it to us.
I chose those because they're nice cut slices, so they're nice representative samples. So when I showed things like condors, so those are good examples. And there's a Martian as well. If you look at that carefully, you can pick out maybe some of the reddish tinges, which are due to the formation of clays and carbonates. So they're sort of more representative, but they are also a sign of, if I'd been giving this talk, I don't know, in about 1981 or so, something like that, when it was first sort of recognized that these were meteorites from Mars, there were, I think it was something like 8 or 9 or something at that time. Now we're well over 100 kilograms, and the statistics are getting quite complicated. So those are from Northwest Africa, hence NWA. So because of the recognition of greater scientific interest and, it has to be said, commercial value, then we're getting more and more meteorites like those. So it's sort of significant from that point of view as well.
Yes, back there.
Thank you for proving there's life on Mars. You spoke about runaway growth. Is it going to continue like that, or will there come a point where it will reverse itself?
Well, I think that stage has passed, but I think we could, I would assume that's what we're seeing in some fuzzy resolution when we're looking at nebula, etc., JWST observations of some of the disks, etc. So for us, that's now switched off. It happened very quickly. Lots of heat sources, very dynamic, and we've got the planets quite rapidly. But that's not where we are now. Yeah. Maybe there's perhaps a nice exoplanet link in there somewhere, I guess. Yeah.
Yes, there's 2 in the middle here, one just along there. That's it. Thank you.
Biologists interested in the origins of life make much of the fact that meteorites landing in the early oceans released organic chemicals. Mm-hmm. Do you see many of them when you analyze meteorites today, and where do they come from?
Well, we certainly do see organic material of different kinds in the chondrites. So, I mean, they're formed from things like, ultimately, I'm not a chemist, but they're things like, they're associated with Fischer-Tropsch reactions in the early solar system. So there are all sorts of interesting reactions related to redox stages between carbon in an oxidized form and in a reduced organic form. So certainly organics were being formed on these early planetesimals, and some may have been interstellar as well, even predating those. So there's plenty of chemistry going on at that point to form those chemicals, thiols, sort of things that astrobiologists are particularly interested in. So is that answering your question, or is it?
The answer is they were all over the place. There's nothing special.
You probably ought to find an organic chemist to give a better explanation, but certainly they're ubiquitous in at the stages I was talking about here, and indeed you find them in the Martian meteorites as well. Yeah, so there's plenty of organics coming down onto the surface of Mars. So when we're looking at the Martian surface and we detect organics, one of the first things that my colleagues on the gas chromatography and mass spectrometer need to, one of the sort of, if you like, null hypotheses is this sort of, primitive cosmic dust with organic material, which has just sort of rained down gently, has been preserved in the Martian regolith, or has it been generated on Mars? So there's that sort of question which is always there in terms of organics.
Yeah, thank you for the interesting topic. Before you said it's quite unusual to find hydrated minerals on the meteorites, and rather than actually the water being on the planetesimals, would you not expect during the accretion that there would be a zone within the accretion disk that contains water, that's fluid water in the right temperature zone in the accretion disk?
Well, we know sort of 5 AU and beyond, then it's much more water and other volatiles start condensing, so you can stabilize ice in some form. It's a sort of it's telling us something, because clearly there was at least at some form, at least at sort of grain boundary level, there was liquid water, which of course is hard to envisage in a vacuum, a cold vacuum. So what on earth is liquid water doing there? So these parent bodies must have been insulated to some extent with heat sources that
something like a massive cloud of water surrounding the, in the right temperature zone, just droplets of water within, space, vacuum, I suppose, yes.
Yeah.
But
Okay,
a large amount, and the planetesimals sort of flying through that zone.
Yeah,
getting hydrated, maybe.
Yeah, water is an interesting topic in terms of planetary materials, early solar system, because the relatively hot inner solar system, we don't expect there to have been much water there because it couldn't condense because the temperatures are too high. So we assume it was out beyond that frost line, but then something probably brought a lot of it back in again. And so that's why I briefly mentioned the late heavy bombardment, which is sort of later than the early solar system, maybe 500 million years after that. But probably you have to bring water back in by some mechanism into the inner solar system.
Question just on the row there, please.
Hi, thank you. There was a recent object identified recently called Uma, which is a cigar-shaped object, which was thought to come from outside of our solar system. And I wondered if you had any comments.
That shows there's still an awful lot more to be seen. Again, 30 years ago, how many known asteroids, identified specific asteroids were there? I don't know, hundreds maybe or something. Now, the statistics are just, they're off the page. They're hundreds of thousands or something. It's only tens of thousands. So the more we get these statistics, the more occasionally, maybe we find something which really has got an orbit which has brought it in from outside our solar system like that. When it first came out, I'd have to say I was a little skeptical. It's not my field, so probably I shouldn't have been skeptical. But yeah, there does seem to be this intriguing possibility that in the sort of primitive planetesimal asteroidal bodies that we're even getting some which originated directly outside our solar system.
I was just wondering if we could learn something about its properties from remote sensing. Perhaps that's... probably...
Yeah, I mean, so asteroids are sort of traditionally classified both in terms of their morphology, sort of onion shell, lead, or rubble pile. Remember I showed that Zag, Brecher. But the main way, I suppose, is spectrally. So from UV up to near infrared. And there are all sorts of different effects like space weathering, etc. But I'm sure there will be, at any opportunity, there will be spectral observations which can help to compare to other asteroids and indeed meteorites to work out some of the processes going on.
Great, thank you.
Any other questions? There's one right at the front here, please. Thank you.
Thanks again for a whistle-stop tour. You mentioned radioactive heating. Are you saying that in the early solar system there was more of this energy source so that the planetesimals could be melted as it seems to be?
In particular the short-lived radioisotopes. So because aluminium is an abundant element, even for one of its isotopes, aluminium-26. So there was enough of it coupled with an amount of energy each decay, and so that sort of energy alone really is enough to cause localized extreme heating, probably getting to the sort of amount of energy released that you could start actually melting this sort of material. Then if you added in to all that gravitational potential energy as well, I think there's abundant heat sources to kick off the whole runaway growth accretion to planetesimal to planetary differentiation process.
That's really interesting. Cheers.
Any other questions out there? Yes, there's one.
You mentioned exoplanets, and my understanding is that the masses and distances from the stars of exoplanets are quite different to the solar system. So I wondered how much that's changed the view of the solar system to make it more unusual.
Well, I mean, of course, there must be some sort of, probably some sort of sampling bias. I mean, there must be. Perhaps that sampling bias will become less problematic with time as we get, move towards the habitable worlds. So that'll be really exciting, JWST. But still, there is a lot of overlap between our giant planets and in the exoplanets, even if they're in strange positions compared to our Jupiter at 5AU. Sometimes they're further in. But I think there are comparisons there that are being made between our giant planets and some of the exoplanets. I mean, it's a bit like the asteroid population. From Kepler onwards, we're just getting this enormously increasing amount of exoplanet information, aren't we? So my guess with time, we start getting into their atmospheres, even direct imaging now. I think we'll see how our solar system fits into other solar systems. So I think we're just going to have to be patient. I think would ultimately be my answer to that.
We've probably got a couple more. So one in the center here, and there's one on the side over there.
Yes, you said some meteorites came from Mars. I'd like you to define that terms. I'm just wondering how they get from Mars to Earth. Presumably you don't mean they were made, or maybe you do, made of the actual planet, or were they just bits of rock that didn't actually make it onto the planet and were floating around? And how do they get from from Mars to Earth? I mean, maybe there's some other. Yes, that's a mystery to me. And,
yeah. Well,
and why do you think it is from Mars when they actually arrive here?
Well, we think they're from Mars because we've got the comparison to the lander and orbital information. There we go. So the main thing you see there, what dominates that map, Mars orbiter laser altimetry map, are the craters. Okay, so most of these craters date from the late heavy bombardment, about 3.8, 3.9 billion years ago. But there's still, there are plenty of impacts since then. And probably something like maybe, well, models vary, but certainly when you have impacts into the crust, onto the surface of Mars, large amounts of it can have so much energy that they are actually can send outside the Earth. They're greater than escape velocity of Mars. A fraction of those, or a fraction of a fraction, if you see what I mean, can end up ultimately in an Earth-crossing orbit. So if you think of all those large impacts, if you think of the amount of material from Mars, from its crust and down into its mantle probably, which were ejected, and then some of that, the orbital characteristics were able to get it to Earth. So they are very much samples of differentiated Mars. Yeah.
It would be if it's impacted by another body, an asteroid, how do you know it's not coming from the asteroid, and from whence does that come?
Because the compositions of the gases trapped in the rocks.
Right. So
Right,
it's just there's a correlation between that. And would some of the asteroid that breaks up, would that escape as well?
Well, the energy associated with large impacts in the solar system like that is so great.
Yeah.
I'm tempted to give a really another anecdote, but I won't in the interest of time and lunch, etc. But basically, the energy is so great that the actual impactor here, most of it is volatilized. Okay, so when the early prospectors in Arizona looked into the Barringer crater, the guy who bought it, Barringer, he did that because he thought he'd make his millions from finding a great iron nickel ore body beneath it. So he kept digging, etc. Never did find it because most of it was volatilized because of the energy. He made his money anyway because of all the tourists, but that's another story.
And one more,
Thanks.
I think there was at the back there, please. Thank you.
Hi. Yeah, I remember maybe 20 years ago there was a paper from the Open University talking about how they discovered life on a meteorite from Mars. Was that something to do with one of your slides? Or was that something else?
Well,
And I
there's the Allen
and I
Hills
presume
84001 meteorite, which was their big controversy with the Mackay brothers. There's been a lot of interest in the organics that we mentioned and the mineral assemblages. I think, piecing all that together, we think we had a habitable, warm and wet environment at parts of Mars's history, where if there was any microbial life, if somehow it got there or it was able to start there, it would have been quite happy. You had the temperature, the water, the nutrients that you need, the sort of if you like, sort of pH and redox sort of envelope. So we know that Mars, that we see here in those ancient crater terrains, was habitable, but the next step, and the reason we want Mars sample return and ultimately even human exploration, is because we don't know if it actually was inhabited. Some of the things that we're finding, for instance, in the meteorites and Mars Science Laboratory, 500 meters of clay mudstone deposits from a lake. You know, this was a habitable environment, but we need Mars sample return to basically answer your question.
Okay, we're going to have to finish it there. Just before we give John a final round of applause, I hope you all noticed Calabrese, McMahon, Bridges, CMB, our very own CMB today. Thank you. That wasn't lost on some of you anyway. Finally, again, John, thanks ever so much.